Entanglement, the invisible threads of space. At the smallest scales of physics, one feature stands out as both strange and essential. Entanglement, the invisible bond that allows particles to share a state no matter how far apart they drift. When two particles are entangled, measuring one immediately tells you something about the other. The unsettling part is that this correlation persists even across large distances, where no signal should be able to travel quickly enough to account for it. Entanglement does not seem to weaken with separation, at least not in the way classical expectations would suggest. Instead, it operates outside the normal rules of space and time that we are used to. Experiments have confirmed this countless times. Photons shot in opposite directions display correlations too exact to be explained by hidden variables. Electrons set into distinct traps behave as if they are still connected, their measurable states lining up as though information flows between them. No classical description can quite capture this. These repeated results suggest that entanglement is not some fringe curiosity, but a basic part of how the universe functions. Some researchers now propose that the connections we observe do not travel across space. They define the fabric of space itself. That claim requires caution, however. It is not that scientists can assert with certainty that entanglement generates spacetime directly. The idea is better described as an active area of research, where evidence and theory point toward space being emergent from deeper informational rules. One way physicists explore this is by modeling entanglement networks mathematically. Individual entangled particles can be represented as links, and when these links scale outward, they form webs that resemble lattices or fabrics. From these webs, large-scale geometry appears to take shape. Theoretical work, particularly through tensor networks such as MERA, multi-scale entanglement renormalization ansatz, has shown how specific patterns of entanglement can mathematically produce spatial geometry. In this view, entanglement is not just a quantum oddity, but potentially the glue binding spacetime together. This doesn't prove the model is final, but it demonstrates in concrete terms how informational patterns could underlie what we experience as distance, shape, and curvature. A single metaphor is helpful here. Imagine a woven fabric. To our eyes, it looks like a seamless surface, but on closer examination, we see the structure. Strands crossing and knotting together into a coherent whole. Without the individual threads, no surface exists. With them, texture and continuity emerge. If spacetime behaves like that cloth, then the continuous geometry we perceive is nothing more than the macroscopic effect of countless entanglement bonds at a deeper level. Remove those connections and the very idea of space would unravel. This perspective helps explain why the universe appears so consistent. Light travels through what seems like continuous fields, gravity bends paths predictably, and events unfold in smooth progression. If entanglement organizes space underneath it all, then spacetime stability is a byproduct of those connections. Stronger networks of entanglement might yield rigidity, while weaker or looser connections could give rise to curvature or horizons. Gravity itself could then appear not as a separate force, but as an emergent result of how entanglement distributes and stabilizes information. Again, this is not a settled theory, but research continues to suggest such patterns could underlie the smooth functioning of what we call physical law. What makes this particularly persuasive is how entanglement shows up everywhere we look. It is not confined to exotic physics experiments or abstract models. Chemistry relies on entanglement to hold atoms in molecules. Biological processes like photosynthesis depend on it to move energy efficiently. The quantum computers being built today use entanglement directly to process information across massive state spaces. None of this is metaphor. It is a demonstration that entanglement is a natural rule of physics, one that technology and biology both rely on. This strengthens the view that what we see on the cosmic scale may simply be entanglement's reach extended across far larger networks. If this is correct, then our normal sense of distance could be misleading. Points that appear far apart when measured with a ruler might be adjacent within the hidden lattice of entanglement. Likewise, two regions that sit side by side in ordinary space might in fact have very weak ties, making them informationally remote. The implications are significant. What we call space could be less real as a standalone thing and more of a projection of these informational relationships. What appears empty could actually be dense with underlying structure. Time may also need rethinking under this picture. If geometry is produced by entanglement webs, then time could emerge from how those webs update. Each reconfiguration would represent a step forward, like a system refreshing itself continuously. What we experience as moments passing may be the network reorganizing states across itself. Instead of an arrow of time imposed from outside, the forward flow might be the cumulative result of entanglement links shifting and recalibrating. A computer program, after all, does not move. It executes line by line. The universe may compute forward in much the same way. Considering this, the long-standing challenge of unifying quantum mechanics with gravity takes on a new shape. If gravity comes from geometry, and geometry arises from entanglement, then gravity itself may be better understood as an emergent property of information. In this formulation, no additional force is required. The pull toward Earth or the bending of light near massive objects could simply reflect how entanglement threads knot and tighten. In regions of extreme density, like black holes, the structure of these entanglement configurations might create the horizons and boundaries we observe. These ideas remain highly theoretical, but they offer a bridge over one of physics' most difficult divides. It can be tempting to compare this to familiar human-built networks. The internet, for example, links computers across the globe. To the casual observer, information moves instantly between locations separated by vast distances, but beneath that appearance lies a web of connections and routing paths. Entanglement might provide something similar, but without wires, satellites, or any infrastructure. The connections asterisk are the structure, and no hidden medium is required. This is not a perfect analogy, but it helps capture the idea of an invisible system producing outcomes that, from our perspective, appear impossible. Taken seriously, such a framework forces us to reconsider the status of both distance and separation. Space may not be a stage where physics unfolds, but a property that unfolds because of underlying informational ties. Entanglement does not merely lurk beneath quantum experiments. It could define the way reality itself holds together. This doesn't mean space is fake, in the usual sense of the word, only that our experience of it may be the surface presentation of deeper processes. Physical separation may be a projection we perceive, while reality at its core could always remain linked through unseen connections. And here lies the deeper point. If entanglement functions as the architecture behind what we observe, then it is as fundamental as any particle or field. It acts not like an accessory feature but like the code itself, weaving the environment in which everything else occurs. Where matter appears, where forces seem to operate, how long events unfold, all of these may be surface effects of entanglement networks stabilizing and shifting beneath. This brings us to a broader puzzle. If entanglement can establish geometry, provide stability, and potentially even explain gravity, then what about the parts of the universe that remain stubbornly unexplained? Physics already tells us that most of the cosmos is made up of something invisible, dark matter and dark energy. If entanglement provides a hidden structure for space, could the unseen mass and energy filling the sky also reflect hidden aspects of how the universe processes its information? That question draws us into one of the biggest mysteries of all. Dark matter and dark energy as the universe's processing cost. For more than a century, astronomers have known that the visible universe, the galaxies, stars, planets, and gas clouds we can observe, constitutes only a small fraction of what is actually present. Measurements of galactic rotation, gravitational lensing, and cosmic expansion consistently show a mismatch between what we see and the forces at play. Ordinary matter made of atoms, accounts for only about 5% of the total. Roughly 25% is attributed to dark matter, inferred from the way galaxies rotate too quickly to be held together by visible mass alone. Another 70% is labeled dark energy, an unseen driver of cosmic acceleration. Together, these two unknowns make up 95% of the cosmos, yet neither has ever been directly detected. They do not radiate, scatter, or interact like familiar particles. In simple terms, most of reality appears invisible. Traditionally, physicists have approached these mysteries by treating them as missing physical ingredients. Dark matter was cast as an undiscovered particle, perhaps heavy and weakly interacting, or ultralight and wave-like, while dark energy was seen as either a cosmological constant or a new force stretching spacetime. These remain dominant views, supported by vigorous searches. Still, a number of researchers have begun to explore more unconventional possibilities. One hypothesis reframes them not as undiscovered particles or exotic fields, but as side effects of information processing on a cosmic scale. In this view, the so-called dark sector might represent the overhead cost required to keep the universe coherent, an unavoidable expenditure in the execution of reality itself. The analogy emerges when we compare astrophysical puzzles with the workings of quantum devices. In a large-scale quantum computer, most of the system's resources are not devoted to the visible computation, but to maintaining stability through error correction. Vast numbers of qubits operate only as redundancy, silently ensuring that the small fraction of logical qubits can function without collapsing. The visible output depends on a hidden infrastructure that consumes greater capacity than the task itself. Applying this lens outward, some theorists ask whether dark energy represents a similar kind of overhead. Its role would not be to propel galaxies by an external push, but to preserve the stability of universal information as it updates continuously. The accelerating expansion might then be an indirect sign of this hidden processing cost. This is speculative, but it provides a frame for understanding why so much of the universe seems invisible yet influential. Dark matter can be cast in equally informational terms. Observations show galaxies rotate faster than visible mass should allow, suggesting unseen scaffolding that binds them together. Instead of discrete particles drifting invisibly through space, one alternative is that this scaffolding is informational, structures that store and preserve the record of cosmic states across scales. Just as a computer relies on memory registers to stabilize its processes, the universe may rely on a vast reservoir that never appears directly, but ensures gravitational systems retain coherence. In that framing, dark matter is less a missing particle cloud and more a structural necessity of computation. Framed this way, the question shifts. Rather than asking, what are these made of, we ask, why does the universe need invisible resources to keep running? As with any computation, the visible output depends on non-visible costs, power consumption, memory allocation, redundancy. To observers within the system, those costs are not seen directly, but their effects are unavoidable. This is a provocative hypothesis, not a resolved theory. Still, it resonates with current data in intriguing ways. In 2024, the Dark Energy Spectroscopic Instrument, DESI, released results suggesting that dark energy may not be constant, but could evolve over time. That possibility directly challenges the idea of a fixed cosmological constant and opens space for models where the energy density is dynamic. Related research has explored holographic dark energy, HDE, frameworks, where information-theoretic ideas are used to describe cosmic acceleration. Some of these holographic models, including interacting holographic dark energy, IHDE, attempt to link dark energy behavior with information bounds and horizon physics. These are exploratory directions, but they show why new interpretive frames, like treating dark energy as a processing cost, are timely. The old picture of a simple, unchanging background pressure is no longer the only option under discussion. Of course, this informational account is not the only explanation. and caution is essential. Mainstream physics continues to investigate dark matter candidates ranging from weakly interacting massive particles to axions to ultralight scalar fields. More complex scenarios, such as inelastic dark matter, propose that hidden sector particles interact with each other in ways that evade detection but match certain anomalies. These proposals remain active, testable hypotheses guiding major experiments. Any claim that unseen matter and energy are purely computational overhead risks overstating current evidence. At best, the information processing picture offers a metaphorical but structured lens to think about why such a large fraction of the universe remains hidden. The strength of the metaphor becomes clear when we revisit engineering lessons. IBM's Qubit systems, surpassing 1,000 physical qubits, visibly demonstrate that overhead dominates. Most of the machine's architecture is consumed not in performing direct tasks, but in making those tasks survivable. In a cosmic analog, the majority share of hidden energy and mass would not be an error or missing element. It would be expected. From this angle, the 5% of visible matter looks less like the whole universe and more like the small output of a much larger underlying system. Yet it bears repeating that this is a hypothesis, not a conclusion. Presently, no empirical evidence shows dark matter or dark energy are processing costs. The most accurate statement is that this reframe aligns with certain data trends and metaphors drawn from computation. Future surveys like Daisy, Rubin, and Euclid will provide critical tests. If dark energy evolves in line with holographic or dynamical models, informational interpretations may gain strength. If it proves static, the cosmological constant remains a strong fit. Either way, observational progress will decide whether these crossovers between computer science and cosmology belong within mainstream theory or remain philosophical analogies. Still, even as metaphor, the idea shifts how we think about the enormity of hidden reality. 95% of the universe as invisible overhead sounds less implausible when placed next to the ratios inside functioning quantum devices, where redundancy outweighs visible calculation by orders of magnitude. It suggests that absence in measurement does not imply absence in function. What is unseen might not be missing, but operating beneath the visible layer as essential support. In this framing, the dark sector no longer poses the paradox of substances that defy detection. Instead, it represents the unseen substrate without which the visible universe would lose coherence. If galaxies hold together, if spacetime expands smoothly, perhaps those observed patterns are the emergent evidence of hidden informational scaffolding. Such an outlook emphasizes not just what we cannot measure, but why invisibility itself might be integral to the whole system. And if dark energy and dark matter are best approached as unseen structural necessities, then we are compelled to ask where else information might hide. Observations already point us toward phenomena where ordinary models break down, such as black holes. Those extreme regions concentrate mass and warp space to a degree that resists explanation, leaving open the question of how information persists when matter falls beyond the point of no return. Whatever dark matter and dark energy ultimately prove to be, exploring these gravitational enigmas draws us closer to the connection between information and the very fabric of reality. The holographic principle, reality projected from information,